So, yes, I'm here from Starling Bank. I'm one of their lead engineers, and I am also the host of the Starling podcast, which you should all listen to. Quick plug there. And today I'm going to be talking about how to build a reliable bank in the cloud with Java. And I'd like to focus on this word reliable because if there's one concern that people have about their bank, the primary concern is security. But I'm leaving that to the security track, so we're not going to talk about that here. The second concern is reliability. People want to be able to, ensure that they can access their money, that their balance shown wherever they see it is correct. They know how much money they've got, the payments they're making are being made and are going somewhere. And that is what they prize. So being able to build a bank that is reliable is a core thing. And even if you're a disruptive challenger bank like we are, you still have to make sure that your bank is reliable and gives the customers that peace of mind they need. And so I'm going to start off with a story that shows how that can go wrong. So, we start on Monday, the 18th of June. And at a major high street bank, I'm not going to name which one, but at a major high street bank, a group of people, our engineers, are preparing to release some code into production. Now, the code they're preparing to release is to change a batch job scheduler. And this is a thing that takes a load of jobs that need to be run in an overnight window, and it schedules them. It says, run this one, then this one, then this one, and so on. So they release the code, and before they release the code, they make sure that everything's in place, right? They make sure that they've got all of the reviews that they need, that the code has been reviewed correctly, all the sign-offs have been done, so the correct people have gone, yes, tick, I'm happy for this to be released out into the wild. They make sure that they've got a backup plan, a rollback plan, just in case everything goes wrong, so they can move back to their previous version. So they release the code, and the release seems to go fine. And then they start noticing some problems. The resource utilization is a bit too high for their liking. There are a few too many errors creeping into the logs. So it's a bit wobbly. They're not too sure about it. And it gets to the next morning, 19th of June, and the decision is taken that there are a few too many errors and they should roll back. So they get out the rollback procedure and they proceed to roll back. And that is when everything goes completely wrong. Chaos ensues. Because it turns out that while they managed to roll back the code successfully, they didn't roll back the changes to their database schema or their data successfully. So, a load of jobs that should have been run were missing. And the job scheduler came along, and it didn't know about these missing jobs. It didn't know that they were supposed to be run. So it just ran all the jobs it knew about. And it turned out that there were a load of dependencies between those jobs. One job had to be run to put the data in place, the correct data in place for the next job to run. But the job scheduler didn't know anything about that, so it just merrily went along its way, running task after task after task, gathering more and more errors as it went. And by the next day, the 20th of June, it was utter chaos. Account balances were incorrect all over the place, payments that should have been made, people weren't sure if they had been made or if they'd been made twice. This had knock-on effects. People's house sales were put on hold because people weren't sure if the bank wasn't sure if their mortgages had been correctly sorted out. So everything was in a disastrous state. In fact, at one subsidiary, things got so bad that the overnight job for the 19th hadn't finished running by the time that the overnight jobs for the 20th started. And you can imagine what sort of nightmare that caused. So, Everything is a complete mess. No one is really sure how much money all the customers have got and whether payments have been made and so on. A total failure of reliability. So they started sorting the data out, and how long do you think it took them to sort it out? Any guesses?
3 years.
I can tell that this audience doesn't really think that banking is up to much scratch. They did manage to get it done in less time than you think. It was about a month, but still, that's not really that good for customers. It doesn't really inspire confidence in the bank when you've got a whole month in which your data has been taken out. So, the question here is, what went wrong? They'd followed all the procedures. They'd got all the sign-off. They'd made sure that the code had been reviewed. They weren't even hubristic. It wasn't just, they were saying, well, nothing can possibly go wrong. They had a backup plan. So, they had a plan to roll back. So what went wrong? Well, what I think went wrong is this. The people in the room knew that failure was an option, but the software didn't. The software did not anticipate the possibility that things could go wrong. So when that job scheduler started up, it just assumed that when it ordered a job to run, that all the jobs that needed to have been run before that would have been run. And none of the jobs that were running bothered to check if the data was in the correct place. They just ploughed on regardless. So all of these different dependencies led to the software being brittle. And this is the problem that I want to address. In order to be reliable, you can't just have the situation where your people anticipate failure, but your software has to anticipate it as well. So now I want to talk a little bit about Starling Bank. Starling Bank, we built a bank in a year, approximately. So we started building the bank in about January 2016, and by January 2017, we were ready to run in a closed beta. So we had, all of the things that you traditionally expect from a bank: the ability to make direct debit payments, the ability to, send money from one account to another, card payments, and so on, and that sort of thing. So we had all of that stuff, and we made it in a year from scratch, from nothing. And then we, carried on. We launched in the app stores, launched publicly in May, and we've been going and building up more and more features since then. Insights on your spending, savings goals, the ability to what we call Starling Pay Me, where you can settle up bills and that sort of thing. So today we have all of these different features and more. I haven't listed them all by any means, but we are carrying on going, great guns with developing all of these new features. So another thing I want to focus on and ask is, how can we have all of these features, deploy them all, keep on coding, and at the same time maintain that reliability that is so important? How can we make sure that we are not destabilizing our code base by going fast with this feature deployment? Now, some of you may have noticed that the title of this track is Cutting Edge Languages. And you might be wondering, hang on a minute, he's talking about Java. He had the word Java in his title slide. Hasn't Java been around for 2 decades or more? Yes, it has. But I'm here to argue that you can still use Java in cutting-edge applications. Now, exactly why we picked Java, I'm going to leave that question hanging open for a while. So we're building up a number of different questions here, which I'm seeking to answer in this presentation. How can you make sure that you maintain reliability and don't go through a disaster like that high street bank I was talking about at the start? How can you make sure that you can develop features and push out loads of features with increasing rapidity while at the same time maintaining reliability? And why do you use Java to do all of this as opposed to any other language? So I'm going to hopefully speak to all of those questions. So next up, I'm going to talk about how we have designed the system at Starling Bank, how we have designed the server back-end code. So we've based ourselves on the principle of self-contained systems. Now, I'm not going to go through every single aspect of self-contained systems. We have the website up there if you want to check it out and read more into it. But there are a number of, and we haven't taken all of the features of self-contained systems, but there are a number of features that we have taken. So the important ones are that a self-contained system owns its own business logic and its own data. So we have a load of services running on the server, and each service has its own code and its own data. It has an API which can be interacted with either by the mobile phones or, for the banking apps, or indeed by other services, but they keep themselves to themselves. So there's no dependencies here. It's a flat structure. So we don't have, one service needs another service to run. They're all independent of each other. And if one service isn't there, the principle is that if another service, if service A is trying to call service B and service B isn't there, service A shouldn't fall over. It shouldn't go, oh, I can't do anything, collapse. It should be able to cope with the fact that service B isn't there. And that's a key point that I will be coming back to later. So, another important point is that communication between these services is asynchronous. So there's this idea which is going to become increasingly important and prominent throughout this talk, which is eventual consistency. So we don't say that the system is instantly consistent all across the board. It is eventually consistent. And this idea that things can go wrong, that you can have something can trip over, and that an action that you're doing might not work all the way through, and that you have to work to get the system back into a consistent state, is going to be an important one. So, as I said, we have each service deployed as an instance, or more likely multiple instances on the cloud. Each one has their own RDS instance, so they have their own database, which isn't interacted with by any of the other services. There's no startup order dependencies, as I mentioned, and the mobile layer, the mobile app, will draw data and information from different services and make requests to different services as necessary. So if you need information on cards, you go to the card service. If you need to make a payment, you go to the payment service, and so on and so on. So you go to different services to do different things. As I said, we're not pure SCS. There are a few ways we differ. So our services, for instance, aren't owned by a single team. We don't say this is the card team and they have to sign off on anything to do with cards. That we do allow everyone to make changes to every single system. And that might change in the future. We might move towards a more ownership model of services. But at the moment, anyone can go into any service and change anything. And there is one key area where we have to synchronize. We try and keep everything asynchronous, but in balance allocation, which is what happens when you try and make a payment on your card. So if you take your Starling card out somewhere and make a payment on it, we have an SLA that says we have to respond within a very short amount of time as to whether that payment can be made or not. And as part of that, we actually have to take the money away. So that is synchronous because of the restrictions imposed upon us. You don't want to be waiting there at the card terminal for everything to become eventually consistent. So there are a few important caveats like that, but for the most part, it's asynchronous, eventually consistent. So here's a diagram of what I've just explained with all of the services talking to each other in that flat structure, not a pyramid, not dependent on each other, and the mobile and what we call the management portal, so a JavaScript web application that we've written for the managers of the bank to interact with that. Those integrate data from different services as necessary. So, we had to invent a name for this sort of architecture, and we invented this handy roll-off-the-tongue acronym, which is Losciaditio, which sounds like a village somewhere in Wales, but is, in fact, stands for lots of, I can't even remember it, lots of autonomous services continually trying to do idempotent things to each other. Great. Who here knows the meaning of the word idempotent? Good. About a third to half of the room. Great. So for those of you who don't know, you can go and look up the definition online, but it can be a bit weird, technical, mathematical if you go and look it up on Wikipedia. But to give you the definition that's important for this talk here, because the word idempotent is going to start to feature a lot. Idempotent means that if you make the same thing will happen if you make a request to an application once, as will happen if you make the same request 3 times. So that's basically the definition we're going to be working with here. So I can sit there and go request A, request A, request A, and it doesn't matter how many times I throw out request A, the command that is associated with that request will only run once. So that's the important principle of idempotency. Now, we'll come on to why that's important in a minute. So, to shorten down this acronym, we have a slightly more comprehensible one, which is Ditto architecture. Ditto standing for do idempotent things to others. And this is the principle that we run the various different self-contained systems, the various different services on our back end with. So they will be able to do things to each other, make requests of each other, make commands of each other, but those will be idempotent. So if the request happens to be made twice or 3 times or 4 times, it doesn't matter. The command itself will only be run once. So, Ditto architecture, the main principle, the key principle you need to think of is the one at the top. Each thing that you want to do is done at least once and at most once. So it's done once. But the reason we separate it out a bit and say at least once and at most once is because you have to put in different systems, different pieces of code, different concepts in order to make sure that these 2 different things happen. And you have to make sure that the at least once thing doesn't try and run it 500 times, and the at most once thing doesn't stop it from happening at all. So there are a few other important concepts up there. One of the important ones is the no distributed transactions. So you've got all of these self-contained systems, and you are running a command across all of them. The transactionality of that is not distributed across all of the different services. It is independently located within each service. What that means is you have to accept the possibility that something could go wrong in the middle. So you could, if you're running something across services A, B, and C, have a situation where it successfully completes in A and doesn't run in B and C. And this comes back to this eventual consistency point. You're asynchronous, something could go wrong further down the line, so you have to be able to catch up. You have to be able to say, did that thing complete? Did that work item complete? So I'm now going to take you through an example of how this works. And we're going to talk about the example of making a payment. So, in order to make a payment from your bank account to another bank account, a number of things need to happen. First of all, let's imagine I get out my phone and now type in that I want to send £20 to someone. A few things have to happen. That request hits the server. Now, the service it hits is a service called Customer. That's the first one. Customer has to do a number of different things. It has to firstly verify that I am me. So I'm trying to send £20 out of Jason's bank account. Is it actually Jason making this request? Or is it someone trying to, steal Jason's money? Secondly, it has to make sure that I actually have £20 to send out. And thirdly, it has to take the money out of my account, reduce my balance by that £20. Having done all of that, and presuming that the verification was okay, it then sends a request to the next service, which is payment. Payment's job is to integrate with the Faster Payments network. This is the network that connects up most of the UK banks and allows you to send payments fast, or faster than they were sent. So that service has to construct a message and send that message off to the Faster Payments network. And the final service involved here is bank. Now, bank's job is to record things in the ledger. So we have just sent off a load of money we've just instructed Faster Payments to send out £20 to someone. So Faster Payments is going to come and collect that £20 from us, because they've sent out the £20, so they're going to present us with a bill later for that £20 and indeed all of the other payments we've sent out. So we need to record the fact that we owe them that money in the ledger so that we can reconcile the bill later on. So each of these systems is following, in order to make sure that things are done at least once and at most once, is following a fairly consistent pattern. The first thing they all do, thing number one, is they do the synchronous bit. And the synchronous bit is to do the minimum amount of validation that you really need to do at that stage, and then log that a request has been made. So a request comes in from the phone or from another service, do the minimum amount of validation, and then you record that in the database. You say, request made to do this work item, and that's it. That's all the synchronous bit done. You've logged the request. Then, generally speaking, very shortly afterwards, but maybe a long time afterwards, you have to anticipate that it might be a long time afterwards, you have to do the actual work that has been requested. And the first thing you do when you do that is you check whether the work has already been done. So we have multiple instances of each service running, so you could end up with a situation where one service has already picked up that piece of work and run with it. So you check again, has it been done? And if not, you carry out the work necessary, and you wait for some sort of response to indicate that that was all okay, that that worked. And if you don't receive that response, then if you receive that response and everything's good, then you mark the piece of work as done and you're finished. If you don't receive that response or something goes wrong, then you go, something went wrong. All right, log the fact that it went wrong, record that fact in the logs, and then don't mark the work as done. And then try again. 1 minute, 5 minutes, 15 minutes later, depending on exactly what you're trying to do, you try again and try to make the payment or send the information to the ledger or whatever it is you were trying to do. So all of them are working with this particular model. And indeed, when payment sends information to bank, for example, payment will say, all right, I've done the work, bank, here's your information, and bank will go, thank you very much, done. And all bank will do at that stage is log the request. It won't try and do the processing, it will just log that the request is there and that some processing needs to be done and return, 202 accepted, thank you. So, what happens if things go wrong? So we can imagine here, this is the failure flow. So we start off with customer doing its validation, checking, taking the money away from my account, and then contacting payment and say, payment, please make this payment, please, of £20. And payment's not there. No response. So what happens? Customer sits round, and then again it tries again. It doesn't mark the work item as done because it hasn't been completed successfully. It tries again, and the second time it tries, things work. And it goes, great, fantastic. So that is the at least once aspect. Customer keeps trying until it gets a successful response. What about the at most once? Now, here what happens is payment makes the call to bank. Now, when payment makes the call to bank, it assigns that call a UID, unique identifier of some sort, to identify the request. And it says, here you go, bank, here is my request, and here is the unique identifier associated with that request. And bank goes, great, and it logs that unique identifier in its database. Now, we can imagine a scenario where bank, for whatever reason, the message back, the response back gets lost. It doesn't come back. Bank's done the work, it's logged the fact that this work item needs to be done, but the response has been lost along the way. So payment's sitting there going, well, it didn't complete. So payment then tries again. 5 minutes later, it goes, bank, here's that payment I needed to make. Please record that in the ledger. And it uses, crucially, the same unique identifier. It says, this work item, 123, please record it. Bank gets that information, and it says 123. Well, I've already logged 123 in my database. That's already there, so tick, everything's fine. And so it doesn't do anything, it just returns 202 accepted. It says, yes, that's done for you, thank you very much, 202 accepted, without actually doing anything. And that's the idempotent bit, the at most once. It's already done that piece of work. Now, here we go into the Java code. This whole system is actually reasonably simple to implement. It can be implemented with two things, two interfaces we've created, or actually an interface and an abstract class. And these are recoverable command and catch-up processor. So, recoverable command asks two questions, which are, what work have I got to do? What is my command? And that command should be idempotently run. And how do I mark that this has been done? How do I record the fact that it has been done in the database? So those are the two questions that it asks. And here, the eagle-eyed among you can read that, is our recoverable command interface with its two methods on it. One asking what needs to be done, and the other asking how do I mark it as done. The second is the catch-up processor. And the catch-up processor is a thing that is scheduled to run every 5 minutes, every 15 minutes, every 1 minute, depending on what you're doing. And it asks two questions. One is, what work items do I need to try and process? And the second question is, what is the recoverable command which I need to use to process them? And the what items do I need to process, we give it about 1,000 items at most to rerun. And we say, here are 1,000 UIDs of the 1,000 work items that you will need to reprocess. And for each one, it will say, great, take that and run it through the recoverable command. And here is the class with the various methods on it to rerun that for you. Great. So we've got this architecture which ensures that we will be eventually consistent. We've constructed it so that if a problem occurs, if something goes down, if one of the services disappears, then everything else will start pinging requests at it, and eventually, when the service comes back up again, it'll be able to take those requests and process them. And if in fact it had already processed some of those requests, then it will just go, well, thank you, I've already done that. So we can be sure that if bits of the system drop out, if particular services disappear, then we won't get catastrophic failure. So we can test this. We've got the ability to test this by killing servers. So we can, try removing all instances of a particular server to see how our system will cope. Or we can recycle them. We can, restart them. And we don't just do this in test, we do it in production. We have chaos technology in production, a la Netflix, which goes around and kills servers for us at random, just says, I am taking this instance and it is gone. And so, therefore we can be sure that there are, we're not just talking the talk, we're actually walking the walk. We're making sure that our service is reliable even when things disappear. And everyone is empowered to do this. So it's not, you don't need special permissions. You don't need, people to come along and give sign off. You can't do that with the Chaos engine because it will just randomly determine to kill things. So this is, the entire organization, all the engineering staff are empowered to go around and test out what would happen if we killed a thing. Because with this Ditto architecture, we are reasonably confident that things will catch up and get back to eventual consistency. Now, this also helps, coming back to one of our earlier questions, how do we keep delivering those features while still maintaining reliability? We can do this continual delivery stuff because we've got the, we've got the ability to go, let's deploy some code to one of the self-contained systems, one of the services. And if that service goes wrong, if something happens that, means that that service goes down or stops processing correctly, we can take it down, we can switch it off, and then we can bring stuff back. We can, bring all of the services back to life and so on, and things will catch up. Things will become consistent. So we deliver in this continuous manner. And when we say we deliver continuously, what we've really done, what we've ended up doing, is turning the two-speed IT processes of most banks on its head. So thinking back to that story I had at the start of the people deploying the code, they will have gone through a laborious process to get that code deployed into production. It'll have been deployed through endless numbers of stages, endless numbers of cycles, and it will have had sign-off from huge numbers of different people going, oh, this is right, this is wrong, change this, do that. You'll have all of this sign-off, all of this ceremony around it. And the problem with that is that it means that deploying code on the back end in the servers is glacially slow. So what ends up happening is that the customer experience in the app or in the web UI, it iterates quite quickly, but it's going over this very slow moving server code. We've turned that on its head. We deploy code to production on our back end pretty much every day, at least once every day, if not more often. So there are small chunks of code going into production all the time. And this we can do because we can, one, take down individual bits of the system because we've isolated them in different services, and because the different services can catch up with each other. So we don't have to wait for ages or have change freeze periods or anything like that. We can deploy code rapidly. We can even deploy it to the stage where we can get people to look at individual commits before we go out and say, is this commit good? Is this commit good? Is this commit good? Because there are few enough commits in each individual release that you can do that. We have something we call the rolling Giffy, and this is Giffy is a plugin for Slack where you can ask it to bring up a GIF of any particular thing. So when anyone is deploying code to production, they will have this rolling Giffy to tell people that the code is rolling and that they should, cast their eyes up at the various exception log monitors and so on to see if anything is going wrong. And I think we've almost exhausted Giffy's stock of GIFs based on the words roll, rolling, and so on. And you can see a selection of our favorite ones there. And if something goes wrong, which inevitably it does, we're not perfect, we deploy code that makes mistakes, those mistakes are obvious. We have a very loud exception track going, there's an exception, a graph up on a screen in our office that says, these are the exceptions happening in production. And you get a very familiar pattern whenever you get a piece of work that is repeatedly failing to run. And that is this pattern you see here. The eagle-eyed among you will see that every minute there are 2 spikes of 2 exceptions each. 2 spikes because there are 2 instances of the particular service that is failing running. And this is being run on a catch-up processor that's run every minute, and there are 2 work items that it can't process. Keeps trying and it keeps failing. But that's okay, because we know that there's a problem. We can get on and fix it, and if we need to do another release, a small patch release into production, that's fine. We can do that immediately. And then, once that happens, the errors will go away, and all of the work that was supposed to happen as a result of whatever command it was that is now failing will catch up, and we will become eventually consistent. So, a case study of this is something that happened to us, I think it was about a month or 2 ago. There was a failed DB upgrade in one of our services called Notification. And as you can guess, Notification is responsible for sending out notifications to customers, either via email or via a message in app or what have you, to say, your payment has been made, or you're running out of money, or something like this. There was a failed DB upgrade which locked the notification database. So it couldn't do anything. It couldn't log any requests or anything like that. So it kept just throwing back, no, I can't do that, no, I can't do that. Now, notification is non-critical. It's important, but it's not going to slow anything down. However, customer obviously started saying, well, I need to send notifications. So it kept going, notify, oh no, wrong response, okay, wait, try again, try again, try again. And this number of work items that it needed to do built up and up and up. And it's got a queue sitting there waiting to send out all these work items. And that queue started filling up with all of these failed notifications. And that meant that other work items that were requested of customer couldn't happen because they were trying to put them in the queue and the queue is full. So things started failing. So what do? Well, we can just kill customer, right? We can take down the customer service, wipe the queue, because all of the work items that need to be done are recorded. So we've wiped the queue, and then we start it up again. And again, it starts filling up, and then we can just reset it, wipe it, and so on. And we can keep doing that until someone comes along and fixes the problem in notification. That means that notifications aren't getting sent out. And once notification is fixed and deployed, then we're in a happy state because the queue will fill up, but then items will start flowing through notification correctly and will be getting marked as done and taken off the queue, not get put back into the queue by customer. All right, so coming all the way back to the start, why Java then? Why do we need to do this in Java? The answer that we have is that Java is good because exceptions are noisy and difficult to ignore. We want the exceptions to be noisy. We want there to be a lot of volume, a lot of spikes on graphs and so on, because then we can see that something is going wrong and we can run over and go, oh, great, let's now fix it. And in other languages, those exceptions can often be less noisy. They can, you have to have explicit handling, whereas Java will, merrily throw exceptions up into your logs for you, and you can measure that. And that's a key part of making sure that we spot errors quickly and are able to fix them. It's easy, there are some other more minor points as well. It's easy to integrate with legacy third parties, and as you can imagine, there are a lot of those in banking. Java, one of the complaints about Java is that it's not very lightweight. We think it can be if you manage your dependencies well. And finally, there's the ecosystem reliability. Java has a lot of users because it's 20 or so years old, 22 years old, what have you, and it has a lot of a big potential job market. So we can maintain reliability on the ecosystem level as well. So just to wrap up, some important takeaways. Firstly, give everything a UID. If you want to implement this sort of architecture, everything needs a unique identifier to be generated, absolutely everything. So make sure you give every request, every item, every payment, every customer, every account, every whatever, a UID, so that you can use that UID throughout your systems to guarantee idempotency, so that you're not sitting there going, I'm going to determine whether this is the same payment based on the date and the amount and the customer. And no, just assign the payment to UID, and then you can ensure that it is the same payment. It's not just hardware that can fail. Hardware can fail, but software can fail too. People can write buggy software, and when people write buggy software, mistakes can happen. So make sure that your code anticipates that. Don't just assume that, don't write code that assumes that everything's going to be fine. Write code that assumes everything's not going to be fine. Write mistrustful code, code that is suspicious and paranoid of failure. Cherish your bad data. We have never cleared down our test systems database, even though it's full of rotten data from half-completed enhancements and developments and so on. Even though it's filled with all these bugs and mistakes, we like it like that because it points out where failures can happen, and it points out what happens when those failures happen. So you can make sure that everything is good. And finally, empower people. You can do anything that you can undo. So as long as you're writing code in this fashion, as long as you're writing code to anticipate and be reliable, and have this catch-upable, at least once, at most once philosophy, then if you want to undo something, if you want to do something, you can do it because you can undo it if it goes wrong. So that's my talk. A quick plug for another talk about Starling Bank, which is tomorrow at 5:25 on the Next Gen Bank track. If you want to learn about the mobile side of Starling, this is the server side. If you want to learn about the mobile side, go and watch that. And that is the end of my presentation. Thank you very much.
Excellent. Thank you very much, Jason. Who has a question? Wielding a mic. Start at the front.
So you have described this scenario when something you depend on, like notifications service, keeps failing, and you are managing this by clearing the state and then probably replaying everything from journal. I'm wondering if this process is automated, or do you do this manually? So you notice that notification service keeps failing for some reason. You can't do stuff, and your queue keeps filling up. Mm-hmm. So your recovery procedure is to stop accepting requests, mm-hmm. and then at some point later recover everything from the journal. Is this whole end-to-end process is automated, this recovery?
So the recovery at the moment is manual, but I'm pretty sure we will automate it in the near future. So we already have automation in terms of we have a number of instances that we want to run in for any particular service, and if that number of healthy instances drops below a certain number, then we'll start bringing more instances of that service up again. At the moment, the problem I described with the load balancer and the queues filling up, that has to be dealt with by us manually killing the services and then having another one automatically brought up for us. But I'm sure that as we go on, we'll start to automate this sort of thing and make sure that we can run it without having to have someone sitting there pressing a button over and over again.
Yeah.
Thank you for the talk. I have a question regarding RDS. You mentioned that you use it, and they have downtimes for the maintenance. So I'm wondering how you eliminate those.
Yeah, absolutely. So we, in addition to expecting that the service cannot be there as a whole, we also have to anticipate that sort of thing that you just mentioned, that the service will be there, the code will be running, but there'll be no database backing it. Now, obviously, if that happens, then when we try and log a request, we can't log that request. So we will return failure, that's out. And having done that, we will then go, oh, okay, that's out, great. Well, stop, try again, et cetera, et cetera. So we've anticipated that being a problem as well. Exceptions will be thrown if we can't get to the database. Yeah.
You talked about self-contained architectures, basically. How are they different from microservices?
That's a good question. So I think that there are a lot of similarities, but I would say that one of the key differences is that it's what I would call a microlith. So it's not a monolith. It's not a thing that tries to do everything, but it is a service. Each self-contained system tries to do a number of different things and has a reasonably chunky architecture and database behind it. But we try and restrict, so it's sort of halfway in between, I would say, those two. It's a good question. I'm sure the microservices guys could give you a better answer than I've just given you, so check with them.
Hey, thanks for good talk. Do you guys use circuit breakers or that type of technology to limit the number of requests you get down to a failing system?
Yes, after that incident I described, we started using more circuit breaker technology so that we could start, stop essentially one service committing a denial of service attack on another service by just constantly bombarding it with requests that it couldn't fulfill. So that was part of our response to that notification incident that I talked about.
Could you elaborate about using async HTTP over like a message bus such as Apache Kafka, for instance? Why you choose async over HTTP and syncing in the database instead of having a message bus such as Kafka?
We found it's less stuff to do. It's less infrastructure to put in place. So we don't feel we need it yet. We might change our minds on that at some point, but at the moment we're just trying to only implement things that we think we need.
Great talk. How do you handle large database updates and data schema updates, or haven't you had to handle that because you're fairly new?
Eventual consistency. So the way we handle large database updates, such as, putting an index on a column on a table that we know to be giant, is that rather than running it at startup time in an upgrade script, we have a background task that we can run at command to put this index in. So we can make sure everything's started up and everything's there, and that there are two instances running, and then we can run the job. And that job will run in one instance, and if that goes bang or something goes wrong, then we can roll it back and consider another approach.
We'll talk about data model updates that could have wide effects on multiple services.
How do you mean?
You want to add a new column, you want to restructure a customer to look differently, you're massively expanding the data model.
Yes, so each data model, or the data models are specific to particular instances, particular services, so they won't cross services. That's one of the key principles of this. So it won't, we won't get into a situation where a change in a data model will affect more than one system at once, basically.
Time. So thank you very much to Jason. Thanks for your questions.